Okay, next, the procedure for analysis. So what analysis that we're going to do? This analysis is on the shear and moment diagrams. So what we want to do is we want to plot this shear and moment diagrams. So first, before you do that, you need to find the support reactions. Okay, find the support reactions accordingly, and then you have to express or write the shear and moment functions, which means Vx, going to do get that letter, and Mx, shear force and bending moment. Shear force is Vx, bending moment diagram functions is Mx. Alright, so we have to look at positive x and all those stuff, how actually the x is positive. So basically x is positive going from left to right, and then only then we plot a shear force diagram Vx and the moment diagram, bending moment diagram Mx. So if let's say later on when we plot it, so it will be something like this. That's just a prelude. V as function of x, or M, okay, internal moment M as function of x. Alright, so if let's say the positive value, you get the positive value, it means that positive value from Vx here in the shear and moment functions. So basically it will be up here. If negative value will be somewhere here, right? Same goes to the internal bending moment diagrams. So if it is positive value, it will be up here, and negative value will be down here, right? So for this example one, okay, this is simply supported beam. You see, simply supported beam. It has a pin support here, and then it has a roller support at the end, and uniformly distributed load W is applied along the length L. Alright, so the question asks to find that to draw the shear force and bending moment diagrams for the simply supported beam as shown below. So how do we do that? So it's very simple. The first one, remember the steps. The first one, you have to remove the constraint here. So you replace with the reactions. Okay, WL/2 going up and WL/2 going up at the end. This you have to do in statics. Alright, we have learned this in statics. You should have learned this in statics. So after we do that, then we try to write the function. Okay, just ignore this for a while and this for a while. Okay, so what we have to do is, how do we find function? So basically what we have to do is we have to cut like this, and then we take left or right. For instance, we take the left portion here, so go here, look here. So what we have is this point A, okay, with the support reaction WL/2, this one, okay, going up. So what we do have at the top of the beam is what? Wx. What is x? X is this line, okay, intermittent line. You cut here x0, increasing, L/2 here in the middle, increasing until x equal to L here. Alright, so what we have to do is just mention as x, because it's a variable now, x. So the equivalent load will be W times x. Remember that. Why? Because this is W, isn't it? This is W, and then because it's just a normal distribution of load, then you just multiply W with x, right? And it should act in the middle, x/2 here, x/2 here, right? And then after we have these two, one support reaction and the applied load, what happened at the section here? At the section here, go back to this one, okay, the positive internal shear and positive internal moment. Alright, where is it? Okay, so for the positive shear, it will go downwards. Why? Remember that the positive shear, the sign convention of positive shear will cause the beam, the section beam, to rotate in clockwise rotation. Alright, while the positive M, positive internal bending moment, will cause the bottom part to be in tension the top part will be in compression. Alright, so these two are the positive sign conventions. So the rest is actually a maths, just maths. So if you do the summation of forces in y direction equals to 0, so you have WL over 2, you see, WL over 2 here, and then you have minus WX, and then you have minus V equals to 0. So, and then you rearrange this, so V will be equals to this. Okay, so this is the Vx. You can have a sanity check for a while before we go to bending moment. You can have a sanity check. What happens if x equal to 0? This x. If x equal to 0, the V will be WL over 2, isn't it? Here at point A, x equal to 0, the V is WL over 2. At x equals to L over 2, this x equals to L over 2, then the Vx will be, the V will be 0, isn't it? So that's why here this is WL over 2 at x equal to 0 at point A. In the middle, the V is 0. Go to the inertial force diagram. Right? As you go along, at the another end will be this negative WL over 2. Right? Okay, so that's one thing. Another thing is about this is for the shear force, and how about the bending moment bending moment. So for bending moment, if you do the summation of moment, okay, here summation of moment, you do, my suggestion, do it at the section. You can do it anywhere, by the way, but do at this section, that you have this V and M, so that the V won't appear in the moment equation. This moment equation, we don't want V to appear, the internal shear. Alright? So if you do moment about the section method, so you have, okay, and then you have to assume positive or negative direction to be positive, whatever. So WL over 2 times X, alright? For the support, the moment generated by the support reaction at A. And then for Wx, you have Wx times X over 2, right? The arm is X over 2 here. And then you have another one is the M. So check this sign, positive, negative sign. I mean, it should be consistent, because here you assume the positive moment to be in counterclockwise rotation, right? So if you rearrange this, then basically you have this M equals to W over 2 Lx minus X squared. Alright? So this is your bending moment function. Right? Mx. So here, sanity check again. What happened here? At x equal to 0, at point A, right? At x equal to 0, let me change to another pointer color. Blue. X equal to 0, so the M will be 0. You see? M equals to 0 here. Same goes to x equal to L, M will be 0. And the maximum will be at x equal to L over 2, in the middle here, the maximum. Okay, if you substitute L over 2 in this M equation, you'll get this Mx equal to WL squared over L, right?